Sorry for this. So this is a talk beyond where and group by. Yeah. And let's start from what everybody knows, and this is that part of SQL that appeared in the very first SQL standard, SQL 86. And this is SQL that select this, as we know, from where, group by, having order by, and limit, although it's not standard, so I didn't put it on the slide. It works, everybody knows that, I hope everybody's using that, that's fine, but really it's SQL 86. It's the time of DOS 3.1. Anybody's using DOS 3.1 here? Well, I don't, you do. Okay, one hand. But actually the technology and software and hardware move a little bit ahead from 86. So why wouldn't we look at what SQL standard has to offer? Why do we need to limit ourselves to this 1986 standard? The next SQL standard that had interesting stuff. And yeah, I'll be talking only about select because it's beyond where and group by, so triggers, storage procedures, all this stuff are completely out of the talk. So the SQL standard was SQL 92, and it introduced the concept of set operations, where every select is looked as a set of rows, and then you can do set operations with them. And union, again, probably everybody knows that it was in MySQL for many, many years. If you have two selects, then union will show both rows that are present in both selects, at least one select. But there were two other set operations introduced in SQL 92, and they were intersect. Intersect will show only rows that are present in both selects, and if you will draw circles like in kindergarten, which are called Venn diagrams, then you will see that, yes, only the intersection of those two circles will be present in the final result set. And except, which it will show only rows that are present in the first select, but not present in the second select. They are both part in MariaDB 10.3. Next SQL standard, which had an interesting feature. It was SQL 99, and it introduced the concept of common table expressions. Now, who knows what is common table expressions? Okay, good. But for others, I'll do a short introduction. So this is subquery in the from clause. If you can see that's a subquery, and it's put in the from clause of the other query. It returns some results, and the outer query returns selects from the result of the subquery. Again, this existed in MySQL for quite a while, and common table expression can say pretty much the same thing, but in a slightly different syntax, where first you specify the subquery, give it a name, and then you select from it. So it's pretty much just a syntax sugar to do the same thing with different words. It does have benefits of better readability in some cases, particularly when you have nested subqueries and it's getting difficult to read. And in particular, when you need to self-join a subquery, then it's much better to use CT, because just imagine this is small subquery, it's in production like 4 pages on your screen. Then you have 8 pages of 2 identical subqueries. You need to scroll back and forth just to see whether it's the same subquery or there's a slight difference in column names. With CT, you just specify it once. But really, it's not much different from subqueries in the from clause, and I wouldn't be even talking about them if not for recursive CTs. So recursive CTs, it's much more interesting feature. It looks like it's almost the same as non-recursive, but in fact, it's pretty much game changer. It allows to do things that were not possible with SQL before, so it's not a different way of saying the same thing. And let's see what recursive CT look like. There's a keyboard recursive in there, and then there's a name of CT, then there's a first select, just like with regular CT, and then there goes union all, and another select, which is defined in terms of this very CT that is being defined. CT is defined using itself recursively, which is why it's called recursive. So how such a thing would be executed? So first, in this recursive CT, we have a select from the folks table where name equals, well, me, and the result gets a row for me. Then we do union all, and we do a join of what was already found, that is the row with me, with the table folks, and that second select finds my father and mother. Then we do another select, the part after union all, and we join this new 2 found rows with the table folks, and we find my grandparents. Then there's another select. These 4 rows are joined with the table folks, and we find 8 more rows, and so on and so forth until the join stops delivering results, until the table folks is exhausted. This is how this recursive CT is executed. So, and you see, this is a This table, it records a tree-like data structure where there's children and parents and their parents and their parents, and traversing recursive data structure in SQL was not possible in SQL standard before recursive CTs were introduced. So they're very useful for these tree-like structures. But also they're useful for data generation. And usually, say you have, which is useful for reports. Say you have an attendance table for some employee, I don't know, a student, and you need to know on what days he's lagged off. Then you would do a left join with the table for all working days for a particular year. And before those CTs, you would need probably to pre-generate this table and fill it in something, PHP for example, with all the days. Now you can generate those tables whenever you need them using recursive CTs. And that, just for the change, I'm not doing working days, I'm doing all weekends in the year 2020. So this recursive CT, it starts from the January 1st in 2020, and then every next row is the previous row plus 1 day. So we will have all the days in this year, and we will continue the generation as long as we stay within the boundaries of the year 2020. So we will have a CT that generates all the days for this year, and then we just need to select only weekends for it, and we'll have the table of the weekends in this year. And you can do it, you can join this table with another table, and you can do some interesting reports from it. And the third example, it's a little more complex example. It's, say, nano-social. It's a very small social network, just 8 people, and the friends table saying who's friends with whom. And I'll show how to work with graph structures using recursive CTs. Say we want to find a chain of friends that connects Chris and Jason. So again, we start with Chris, and then we start with the Chris name, and then we start append friends to it until we get a chain to Jason. So we join, for every next row, we join the previous row with the table friends to find the next friend. And because we don't want cycles in our path of friends, we make sure that the new friend is not already in the path. And if you have found such a friend, we just append it to the path, and we will do that until we reach the user with the ID equals 4, which is Jason. So if I run this CT, I'll get all the possible paths between Chris and Jason. There's 3 short paths and 2 a little bit longer paths. So that's how you can do graph structures in CT. So as a summary, there are non-recursive CTs, and they are not very interesting. They are just a different syntax for subqueries in the from clause, although they are more readable, and in some cases, depending on the implementation, they could be better optimized than subqueries in the from clause. In recursive CTs, it's a totally different thing. It allows you to do things that were not possible with SQL before, so no new possibilities. It allows you to query hierarchical data and graphs and trees. It can be used for data generation on the fly whenever you need them. And they actually make an SQL, so I've heard, a Turing complete. So if you Google, you can find CTs that solve Sudoku, that do brainfuck interpreter in SQL, and other crazy stuff that you never want to do with SQL. Now again, fast forward, next interesting SQL standard, SQL 2003 introduced the concept of window functions. So what are window functions? First, just shortly, what other types of functions exist in SQL? So there are normal functions in SQL. They are invoked one per row, and they deliver as many results as there are rows. So if you select a table from a table, you get a table of 10,000 rows, and you use normal function like concat or MD5, then you'll have 10,000 results. There are group functions, there are aggregate functions. They're invoked one time per group. They deliver one result per group of rows, and the result depends on the whole group. So if you have those 100 groups of 100 rows in each group, the normal function will deliver 10,000 results, while aggregate function will have only 100 results. And window function, there's something in the middle. They deliver one result per row, but the result depends on the whole group. So they don't have that tunnel vision looking at every row. They can see all rows around it as well. And about all rows around it, this is example to explain what is why they're called the window functions. It's typical example. It's called a moving average. If you have some data that fluctuate, they have high frequency noise and then change slowly over time, and you want to see this slow changing pattern, then you need to remove the high frequency noise. And this is often can be done using the moving average. Basically, for every data point, you take few points around it and you average them all and put it inside of this data point. And to do that in SQL, if you ever need to do that in SQL, because usually it's not done in SQL. You just need to calculate the average. You calculate the average for all rows starting from 2 rows before the current data point and 2 rows up to 2 rows after the current data point. So you have a moving window that moves with the current row, and that's why they're called window functions. And you run average for rows within this window. A more practical example, something you're more likely to be doing ever in SQL. This is data for hypothetical example bank, which stores not database transactions, but financial transactions in a table called transactions. And every transaction has a transaction ID, a customer ID, and amount of example monetary units, which I'll call coins here because it's the hype of the day. So, and this table, in table transaction stores what users did what transactions. So in the first transaction, first user took 50 coins out of his account, then third user put 50 coins into his account, and so on and so on. And say we want to know the balance on each account after every operation, something like this. So after the first user took 50 minus 50 coins, the balance is minus 50. For the second is plus 50. Then first user put 950 on his account, the balance will be 900, and so on and so on. So how can we do this in SQL? This is possible. It's not even very difficult. We just need to write a subquery that will sum all the transactions for this particular user with the transaction ID that goes above and up to the current transaction. So summing all those amounts, we will get the running total, and it works. But yeah, so what are the problems with this approach? First, it's not difficult, but it's not exactly easy either. So to understand what this subquery is doing, you actually need to look at it and you need to turn it in your head a few times, trying to understand that you sum for this user, and then you understand that it's running total. And how this subquery would be executed. So for every row in the result table, the server would need to read all the rows in the table, find rows with the correct customer ID and correct transaction ID, and then sum them up. For every row, it needs to scan the table and read the rows. So complexity will be quadratic, and if you have the table 10 times larger, the query will take 100 times longer. So it's not always a practical approach. On the other hand, you can do the same thing with SQL, with window functions, where you need to, with window function, you need to sum all the rows, and the window will be between unbounded preceding, that is from the very beginning, and up to the current row. And this is, by the way, a very rare, if not unique, case where SQL standard is not very unknowingly verbose, because this is the default behavior, and you can just omit the window specification. And then you get a very concise subquery, very concise query. So it's first, it's a lot shorter to write, and it's easier to read because you immediately see that it's running total. But the most important part is that that server, MariaDB, whatever, also understands that this is running total, and it will not need to do a subquery, because how would you do the running total with pen and paper? When you see a next transaction of the user, you take the previous balance and you add the amount of the next operation. So you don't need to read the whole table every time to calculate the balance for every row. And this is exactly what MariaDB would do in this case. For every new row, it will take the previous balance, it will add the current value. So it will not do this scanning table for every row. So and it will be linear complexity. If you have your table 10 times larger, the query will take only 10 times longer. And I did short benchmarks directly on this laptop, not very scientific. But you can see that subquery approach, it gets totally unusable very quickly. So it's 3 hours for 100,000 rows. And then I put an index on that, the best possible index tuned for this particular subquery to make the most of it. And it helped a lot, and the query became actually useful and usable. It could be used up to 100,000 rows. But still, the query execution time grows rather quickly. And I would think that if I would add 100 times more rows, it would be just as unusable as the first subquery approach. On the other hand, window function, it grows. It's not only always much faster. It also grows much slower. So even if I would use a 100 times larger table, it would probably be perfectly usable, even with the tables that large. So what are window functions? Window functions, they provide a useful way to avoid slow subqueries and self-joins. They provide better readability, and more important, you can better convey the meaning of what you want to do to the optimizer, so it can optimize the query better. And that results in much faster queries. Now, fast forward in time, we get SQL 2011, and this Colin was right. System version tables introduced in SQL Standard 2011. So what are those system version tables? Let me describe through rather different problems that could be solved with system version tables. So I don't know if this ever happened to you. It did happen to me quite a lot, although not really in MySQL command line prompt, but yeah. If you mean, there is a real use case for undoing statements that you didn't actually want to do. Another use case would be doing analysis on historical data, comparing how did your user base change this last year, what people were buying 2 years ago compared to what people are buying now, or what ads they're clicking on, or I don't know, what hotel rooms they're booking. And the third use case is if you look at your logs and you find out that for some reason you had a data breach half a year ago and you didn't actually notice that, and now you need to dig it up and you need to understand what data might have been leaked and what users need to change their password and so on. That's forensic data analysis. And these use cases all can be solved with system version tables. But this is not the case when SQL standard is not unknowingly verbose. So let's take, this is a normal not system version table, and let's make a system version. So according to SQL standard, first you need to add 2 columns which are timestamped with microseconds. They're generated columns, and the first one is generated always as row start, and second is generated always as row end. Then you need to add a special incantation, a period for system time with those 2 columns. After that, you need to specify that this table is created with system versioning, and then you have a system version table according to the SQL standard. And we in MariaDB thought that first is a little bit too verbose to our taste, and second, when you do select from that, you just want to have the table system version. When you do select, you don't really want to see those timestamps. They're just garbage because you want to see real data, but version. So this SQL standard syntax, it's optional, and you can drop it, and the table will still be system versioned, and you just won't see timestamps in your data, in your output. And why would you want to do that? Because if you have a system version table, then you can do this magic thing. So you select from the table, and you select from the table, and after the table name you specify for system time as of some specific point in time, and you see the data as they were at the table at that point in time. And this solves all those 3 problems that I just mentioned, because if you accidentally deleted all your data in the table, you can just insert into the table the data as they were in the table 5 minutes ago, and the data are as good as new. And if you want to do analytics on the historical data, you can join this table with itself from 1 year ago, and again you can compare the data and derive some useful conclusions out of that. And if you want to know what an intruder saw half a year ago, all you need to do is select from the table at exactly this point in time that you hopefully have in your logs. And then you see exactly the data that he was seeing, and you will see what users existed at that time, what users didn't change their passwords since then, and then you can alert them and do some damage control. Yeah, we'll have other extensions to SQL standard. I'll just only mention one, because history might take a lot of space. You might want to store the historical data separately from the current data, because most of the time you'll be working with the current data. And by partitioning by system time, you can keep the history separately, so that accumulated mass of history will not slow down your day-to-day operation with the current data. The next SQL standard the new feature, new SQL standard, it's SQL 2016. That's the very new SQL standard, and it introduced operations for working with JSON. So this is how a JSON looks in SQL standard, and these are SQL standard functions for working with JSON. There are not many, and the last one is not yet in MariaDB or MySQL, but although there are plans to do that, in MySQL there's lab release even with JSON table. But it's still a very small Spartan set, so both in MariaDB and MySQL there are lots of other functions to do something useful with JSON, to modify it, to query it, to get some JSON metadata, and the last 3 functions to reformat JSON in compact or loose way, although they're only in MariaDB, they're not in MySQL. But I won't be talking long about JSON, because everybody knows what JSON is, everybody has seen JSON, so I just skip it. And the last part is not in any SQL standard at all, although eventually someday might be. This is new feature appeared in MariaDB 10.3. This is aggregate storage functions. So you can do create function and create aggregate functions, not aggregate function. And to explain me the syntax, first I start with a not aggregate function. That's perfectly standard not aggregate function that reads all data from a table and calculate the sum of squares for a particular column. So it creates a cursor for select. It reads rows 1 by 1 from the table. Then the table is exhausted. Continue handler jumps in, and it returns the sum of squares. That's perfectly standard. Nothing new should be around here. And that's how we do an aggregate function out of it. So that's a keyboard aggregate. And then there's no accumulator here, but there's a parameter for the aggregate function. And no cursor. Either cursor is implicitly created, and there's a special incantation, fetch group next row, which reads a new row for the current group. Everything else works exactly the same as for non-aggregate function. It reads the rows. When the group is exhausted, continue handler jumps in, and it returns the accumulated sum of squares for the column X. And to show the usability of it, this is an example how to do a median completely in SQL using custom aggregate functions in SQL. To make it easier to read, I highlight you need to start reading from this one because this is where the execution starts. Then it does the loop inserting data into the table, and when the group is exhausted, continue handler jumps in, it picks the middle row from the table and returns the median. That's how you do median in SQL in MariaDB 10.3. Questions?